So we're going to start with the homework for chapter 8. If you have already completed all of the homework, just bear with me while I go through some of the highlights before we start chapter 9. So Kelsey, I think you finished chapter 9 even.
Oh,
so,
no, I haven't finished chapter 9.
Oh, okay. So we'll get there. Now some of the questions are fairly non-problem. In other words, you can look them up. There's not a lot of reasoning. You can simply look in the notes or in the book or in your notes if you take notes. Now here we have one more chance to remember how these chemical equations actually not only give you amounts in moles of every chemical involved, but they can be used to generate conversion factors because of the relationship between every component of the equation. So let me explain. When nitrogen dioxide reacts with water, it always reacts in a 3-to-1 proportion. So we said last week, if we have 6 moles of NO2, then we can consume or react 2 moles of water. If we double that, we double that, we double that, and we double that. Everything gets doubled or tripled or cut by half. That's what I mean by being proportional and by having these relationships possibly available as conversion factors. Now this one is asking for the number of atoms of oxygen in the reactants and in the products of each of the following equations. This is a little bit of a loaded question, if you will, because I could argue, and you could argue, that this also represents atoms or molecules. I could say, well, 3 molecules of NO2, not moles, but molecules, react with 1 molecule, not mole, of water. So that is in fact correct. However, I think what the problem is asking state the number of atoms of oxygen in their reactants and in the products for each of the following equations. So we need to count oxygen atoms, and they want a total number, I believe. So we're going to have to try it. Now, how do we count that? Well, remember the coefficient affects the entire molecule. So it's 3NO2, not only 3N. 3 times 2, that's 6 oxygens. So I would argue that there are 6 oxygen atoms here, plus 1 here. So that's 7. Now, do they want the total number? So 7 plus whatever is on this other side. 1 plus 2 times 3, 6, another 7. Do they want 7 or do they want 14? When I say they, I mean the system. So I'm going to put 14. And hopefully we'll get feedback to see if that. So you have entered the total number of oxygen atoms in reactants plus products. So, well, that's what I thought the question was asking. Let's go back. State the number of atoms of oxygen in the reactants and in the products for each of the following equations. Last time I remember, and means plus. In statistics, it sure does. So let's see, 7 is my second guess. I hate it when these questions are a little bit more cryptic than what it is. So when you read the question again, perhaps if I were to rewrite it, I would say state the number of atoms of oxygen in the reactants, and that's it. Not even add and the products. Or state the number of atoms of oxygen in the products for the equation. Because when you add the word and, that implies addition, right? So my apologies. I will give feedback to the people who put together this question. The good news is that you have multiple attempts. So going forward, we're going to answer that way for the next parts. So there's no oxygen here. There's 2 times 2, 4 oxygen atoms. That's all we're going to say. And submit. So there's 2 more reactions. I don't think it's necessary for us to solve them. The previous one had a little triangle on top. Remember that that little triangle means you have to heat up this plus that, add heat for that to occur. So it doesn't go spontaneously just by mixing. It needs that extra push of energy by adding heat. Any questions about that problem? Okay, let's go to number 3. So once again, here we had to probably answer on only one side. State the number of atoms of each element on each side of the following equation. On each side. So maybe we need to go all the way through, but they only list these 3. So that's, once again, I think is implying that we need to add them. How many carbons do you see here on the reactant side? I see 1, right? 1 carbon. So we're going to put 1, and then how many hydrogens do we see? 4 on the reactant side. I'm not considering the product side. And then how many oxygens? 4. Also 4. So let's try that answer and see what happens. So 1, 4, 4. That's what I'm submitting. And that's what they wanted. So once again, what we figured out on the previous question applies to this one. They don't want you to add them together. They just want one side. Before we move on, let's see if it's a balanced equation. So 1 carbon, 2 oxygens plus 2 times 1, 4 oxygens, and then 2 times 2, 4 hydrogens. So it appears to be balanced.
Do you think it'll affect it if it's not balanced for another question?
Well, it would, because in fact, I think that would mean that we need to either add them all together or choose one side or the other. So yes, that's an excellent point. It better be balanced so that we have only one and only one answer for either side. Beautifully put. I mean, that's a good comment. Okay, so very quickly, I'm not going to write them down. There's 4 P's and 10 O's. Would you agree with that? Okay, so let's move on. Nothing complicated there, nothing complicated there. I mean, if you have a molecule like glucose with a lot more atoms, you still just add them together. So 6 carbons total, 12 hydrogens total, 6 plus 12 more, 18 oxygens. So that's a lot more than before. And it should be the same on the left. 6 times 2, 12, plus 6, 18. Okay, so let's take a look at the next one. I think the idea is to be building confidence as far as being able to interpret what those coefficients are and how they apply to the different parts of a molecule. So in this case, we're multiplying coefficients by the subscripts of every atom. Now, that question is a little bit more clear. Determine whether each of the following equations is balanced or not balanced. Only two choices. We need to still account or count atoms on both sides of the equation. And keeping track of them, we have one sulfur, right? Sulfur is balanced. We have two oxygens on the reactant side, but we have three on the product side. So this equation is not balanced as written. It has the correct formulas, but it doesn't have the coefficients that are required. So before we move on, I hope you see that you can balance it by adding a 2 in front of the SO3, which will force you to add a 2 in front of that, and which will also force you to say, okay, so 2 times 3 is 6. I need a 3 here. Trial and error always is going to give you the answer. Okay, we can look at this fairly quickly. I'm going to stay here. Magnesium and magnesium not balanced, right? If you have any objections to what I'm counting here, please do let me know. P and P, 1 and 1, that looks balanced. 3 chlorines plus 2 is 5. 5. So this looks balanced, right? And this one, let's just do it because it has hydrogens in different places. 1 carbon, bless you. 1 oxygen, that's good so far. 2 times 2, 4 hydrogens. 3 plus 1, 4 hydrogens. So it appears to be balanced. Okay, number 5. So now we are told that all of these equations are balanced, and we are asked to state the number of atoms of each element in the reactants and in the products. Once again, they probably need only one side. So let's just do one to make sure that that is in fact correct. I'm going to move to the second one. So we have 1 phosphorus on the left. We were already told that is balanced. 3 chlorines on the left and 6 hydrogens on the left. So 1, 3, 6. And that's what I'm submitting. So yes, no addition required of the reactant and product side. Okay, number 6. Okay, so definitely when you answer this question, check against your reference, against the list of 5 reactions that we produced. No need to memorize these things. Now, some of the names are quite revealing. Combination obviously means combining. The composition, I hope by now you know that it means breaking apart. And then single replacement, we'll take a look at what that may mean later. Here you have one molecule, a second molecule on the reactant side, yielding one single molecule. So from 2, you get to 1. What would we call that? A combination reaction. So it's not a combustion. A combustion, is the only one that I would say memorize. In a combustion, there's always oxygen on the left, which this appears to qualify. But there's also always carbon dioxide and water on the right. Not to mention the hydrocarbon, but that's oxygen on the reactant side plus CO2 and H2O on the product side is a combustion. This one doesn't have that, so we're going to say combination. Oh, that was one only. Okay. in balancing a certain equation, you find that there are 4 phosphorus atoms on the product side. Okay? I think I better write this down. 4 phosphorus. The only reactant is Mg3PO4 2. Mg3PO4, 2 of those. Which of the following answers shows the correct way to modify the formula Mg3PO42 to give 4 phosphorus atoms on the reactant side of the equation? Okay. Which of the following answers shows? So remember that if this is the correct formula, we cannot touch the subscripts. Those need to remain. The only thing that we can do is put coefficients. So the only one with a coefficient is this one. That would tell me immediately that's the way we have to go. Now, cleverly, and trying to distract you, they put a 2 as a coefficient in front of that, but that breaks apart the formula of the molecule that we were told is correct. So that cannot be. Now, if I put a 2 in here, which is the only option with a coefficient, and then I do the math, I have 2 times, there's a 1 here, but a 2 here, so 2 times 2 is 4. That gives me the 4 phosphorus that they implied in the question. So I'm confident, I hope you are too, that that has to be the answer. On 2 accounts. Not only because it's the only one with a coefficient, but also because that gives you the correct number of phosphorus for the product side. Okay, so tricky question in some ways, but I think we can rationalize it. Okay, we're halfway there almost. Now we're going to be balancing. So in order to balance the equations, they want the answer box to have the whole thing. So we're going to have to use the different tools to write it. Now let's first balance it on the board. Or maybe you already figure it out. It doesn't appear to be balanced. There's 2 nitrogens on the reactant side and only 1 nitrogen. What can we do?
Put a 2 in front of the oxygen and then put a 2 in front of the final product.
Okay, so a 2 in front of the oxygen would give us a 4 on the reactant side. And if I put a 2 in front of the NO2, that also gives me a 4 on the oxygen. And because I have 2 over here and I added a 2 there, now I also have 2 nitrogens on each side. That looks like the right way to write it down. Now, because this thing has multiple ways of writing different things, let's just make sure that we enter it correctly. So we want a template for a subscript. Oh man, I don't know if I'm going to be able to see. Oh, there it is, okay. A 2, I'm going to click to get out of there, open a parenthesis, put the letter G, a plus sign, and then you said a 2 in front of the oxygen. Capital O for oxygen. Now we need the subscript 2. Let's get out. Apparently there's an arrow here. I think because I made the screen bigger, they're not showing up as nicely. So that's why they are, oops, disappearing. And now we have, Caitlin, you said 2, right? So 2, capital N, capital O. Oh, I forgot something here. I need to put gas. Oops. And now the subscript for the oxygen, and then the phase. And I think that's it. Now on this one, let me just take a look at the templates. Is there a triangle somewhere in there for the heat? So no way of indicating heat. I'll come back to this one if there's plenty of time, but the rest is just the same. Enter a balanced equation using the correct formulas and include conditions. Okay, so this is now getting almost to the higher level of understanding, because it implies that you need to remember how to write formulas from names. And for that, you're going to have to look it up. I mean, you can, I'm not going to be saying you should not look it up via Google or any other internet search, but you do have the tools to know that calcium carbonate has calcium, Ca, and carbonate is one of those polyatomic ions, I believe it's CO3, that carbonate has a charge of 2 minus. So this is 2 minus, this is 2 plus. Crisscrossing gives me 2's and 2's, which I can simplify. So that should be the formula for calcium carbonate. Decomposes. So this is going to be a decomposition reaction to produce solid calcium oxide. So all oxides have oxygen, so I'm going to put an O here. I also want to remind myself of the charges. Oxygen 99.9% of the time is going to be 2 minus when it's combined. When it's by itself is 0, but when it's combined with another element it's going to be -2. So that should be the right formula for calcium oxide, plus carbon dioxide. This is one of those that maybe by doing it so many times we already know that it's CO2. I don't need the charges to know if that's the right formula. So let me erase those distractions. And I'm not done, because I need to put now the phases that were mentioned in the statement. So solid calcium oxide is also a solid. Our carbon dioxide is 99.9% of the time a gas. So it is indicated as a gas. And now we need to balance it if it's not balanced. So 1 calcium, 1 calcium. Because carbonate doesn't appear on both sides of the equation, we cannot balance it without breaking it apart, so we need to count each element. 1 carbon, 1 carbon, 3 oxygens, there's 1 there, plus 2, that's 3. So it appears to be balanced as written. Now we just have to just do it once here, using the templates. Then it's a solid, and it just decomposes, so there's no need for a plus sign. Calcium oxide, also a solid, plus, and that's the decomposition, CO2 with a subscript, and a gas. A little time consuming, but that's what we're submitting. always read the feedback, because it really tells you, some information that was covered in chapter 6 and 7, and it's always good to remember. If there's a metal, you have an ionic compound. That you better remember 10 years after you finish this course. Ionic compounds have metals. Okay, now, here we are in oxidation reduction. If we use one of the two little sentences that I gave you, Leo the lion goes grr, or oil rig, I think we can fairly quickly tell what's going on as far as the loss of electrons or the gain of electrons. So copper here, which is not written but has a charge of 0, is becoming more positive. In other words, it lost electrons, so it oxidized. Silver, which has a charge of +1, and it doesn't show the 0 here, gained an electron, so it got reduced. And what's the question? Identify the reactant that is oxidized. So copper is getting oxidized, right? So we're going to say copper. Wait a minute, the reactant, yes, submit. So be careful, because if they had said identify the product that was oxidized, then you need to look at the product. And in this case, the one that got oxidized was silver in the product side. Okay. So this chapter deals with chemical quantities, and it's not going to be always in moles or atoms or molecules, but quite often in grams, because that's what makes sense in the real world. When you work in the lab, you work with grams, not with moles. I just saw 7 here. 7 is a pesticide, so what is going on here? So they have an introduction, oh yeah, in which they are testing water samples for insecticides. And of course the movie is fiction, but it's an interesting take on chemistry. Okay, from conservation of mass, we're going to move to more relationships in chemical equations. We've done many related things to that when we balance equations. So we're going to be in good shape. Now, mass calculations for chemical reactions is something that we're going to also continue to do. Here is where we enter the more difficult part of the entire semester, which is defining limiting reactants and talking about something called percent yield. I implied the idea of limiting reactants earlier when I was telling you about making pancakes at home. If you have flour and egg and milk and combine them, you get pancakes. But there's a certain proportion of these ingredients that you need to be combining. You don't just randomly combine them. And in my example, I think it was 1 cup of flour plus 1 cup of milk plus 1 egg gave, I don't know, 6 pancakes. So this is milk, and this is flour. When we talk about limiting reactant, well, you're going to be learning that if you want to make 12 pancakes, you're going to need 2 of these, 2 of that, and 2 of those. But if you only have 2 of these, 2 of these, and 1 egg, the egg becomes a limiting reactant. You cannot make 6 pancakes if you only have 1 egg. I mean, you can, but they're going to be horrible. you need 2x. So we're going to be identifying the so-called limiting reactant. Okay, all of this stuff we already know. So we are, again, in good shape. But let's take a look at this example. Because we've been asked to do masses, not atoms, not moles. And you're going to have to remember that you need the molar mass to find the answers to some of these questions. So here we have, I think I have enough time for one example. 4 potassium in the solid state reacting with oxygen in the gas state to produce potassium oxide. All of these are the right formulas. We alluded to these last week. But essentially what we're going to do is we're going to look at the molar mass of each component and make sure that the balanced equation that we have written here agrees not only in moles but in mass, in grams. So what is the molar mass of potassium? We have 4 mole of potassium, but we need to multiply that by the molar mass of potassium. And according to the periodic table, that is 39.0983. I'm going to go with 39.1 for this example. Grams of potassium per 1 mole of potassium. So if I carry out this operation for the coefficient multiplying the molar mass of potassium, that's going to give me the total amount in grams of potassium on the reactant side. So 39.1 times 4, 156.4 grams of potassium. Now, still on the reactant side, we have 1 mole of oxygen. So we have 1 mole of O2. We need to find the molar mass of O2, not of O, but of O2. So if we go to the periodic table, we have 16 for oxygen, but this is O2, so there has to be 32. So times 32 grams of O2 per 1 mole of O2 is going to give me the total amount of oxygen in grams. So that's 32. If I add those two together, I have 4, I have 8, 188.4 grams. Now, on the reactant side, we have 2 mole of K2O. We need to multiply that by the molar mass of K2O. To save time, I'm going to ask Wolfram Alpha for that information. Uh-oh, it went the math way. $94.196 grams of K2O per mole of K2O. So 94.2 times 2 is going to give me 188.4. So that's conservation of mass. On both sides of the equation, we have, where is the book? 188.4 grams. And this is an example from your book, so you should have an answer somewhere. No, it doesn't. Oh, check answer yes here. And that's exactly what we found, 188.4 for the first exercise. We'll continue on Thursday with the second part, and then we'll move to the more challenging part of limiting reactant and percent yield.